Hi folks, welcome back to Physics with Captain Rod. The topic of this video is going to be Bohr theory or Bohr theory of the atom. So before we get into Bohr theory, I'm going to talk a little bit about the background of it and where it came from. So what we're looking at the left here is some sort of light bulb filled with a gas, maybe hydrogen, neon, or could be any one of a half dozen or more different elements. And one thing that's pretty well understood now and back, in the time of Niels Bohr was that if we supplied energy here, we supplied a voltage to this gas and ran a current through it, then we know that we get light out of it. This thing would basically, we'll say, glow. And what I did here is I drew one. This represents just one light ray, right? But imagine, there's like, you could imagine it as an infinite number of rays going in all directions. So we know that we can excite a gas and make it give off light or electromagnetic radiation. Now, it was found at the time that if we take one of these rays and we run it through a prism, so hopefully you've seen my videos on refraction and how prisms work, but what happens is that the light, which is generally considered to be white light, will get refracted through the prism, and basically what that means is it'll get spread out a little bit so that when the light leaves the prism, what we see on the right hand side is the rainbow. So everybody's looked through a prism, hopefully, and you've noticed this effect. You look through a prism and you'll see all the different colors. An interesting thing occurred, though, that when people looked at light from just an individual gas, like maybe hydrogen or maybe just neon, what they found is that they saw kind of the rainbow over here, but it wasn't complete. They found these narrow little bands. So when you take light from something like hydrogen and you scatter it or spread it out using a prism, and you project it on some sort of screen, or I'll just say we observe it from over here, what you see are these just narrow bands of different colors with nothing in between them, right? So you don't see a continuous spectrum. So this puzzles scientists. People are like, what's going on there? Right? Because when you take normal white light from an incandescent light bulb and you run the same experiment, what you'd see over here would be more continuous. You'd see red and it would bleed into orange, which would kind of change into green, blue, violet, etc. And it wouldn't have these gaps in it. But that's not what you observe if you look at light directly from hydrogen or neon or some other gas. So Bohr theory is the first theory to try to explain this phenomenon. So if you give me a moment here, I'm going to clear this screen. Actually, I'll just do a new one. All right, so now we're going to dig into what's happening at the scale of the atom here. So atoms have a central location called a nucleus. And for this discussion, I'm going to limit myself to hydrogen here. Now, the fundamentals that I'm going to talk about are true for all atoms, but hydrogen is one that's relatively simple and we can actually attach some mathematics to. So a hydrogen atom basically is a positively charged nucleus circled, I'm going to go ahead and do kind of a nice circle here, by an electron, a single electron. So here's I'm going to just put, oops, give me just a moment here. I'm going to just kind of put the path here, this kind of circular path. And on that path, I'm going to put an electron. Now, again, this picture is not to scale. Again, if the nucleus of an atom were this big, this first distance here is astronomically many hundreds of meters or more, and you wouldn't even be able to see an electron. But so a hydrogen atom has a single positive charge in the nucleus, and it has an electron orbiting around. Now, these electrons can move to higher orbits, and there's a mechanism for that, right? And that mechanism is by absorbing energy, and one way to do that is to absorb the energy of a photon. So if we picture like a higher up orbit, if this electron absorbs a photon, what it can do is it can itself move up to a higher orbit. However, this is a naturally unstable site or position or situation. State, that's the word I'm fishing for. This is naturally an unstable state. Technically, one could say it's kind of there's an equilibrium there, but it's what's called an unstable equilibrium. All systems tend to move towards their lowest potential energy state. An example of that is if you take a pencil and you try to balance it on its tip. Technically, there's an equilibrium position there, but you'll never find it. It will always fall back over. Systems naturally want to move towards lower potential energy. So this electron is going to move back down, no doubt about it. Oops, do that in black. So this electron is for sure going to go back down to its original potential energy state. Now, when it does so, it'll give up a photon. So what you have to realize here is that when an electron absorbs a photon, it increases its energy and it goes to a higher orbit. When it comes down back to its ground state or its lowest energy state, it will give that photon up. Now remember that photon energy is dependent on frequencies. So let me kind of back out of here. So the energy of a photon, let me do that in black, is directly proportional to the frequency, and the proportionality constant is called Planck's constant, 6.63 times 10 to the minus 34th. I'll write it down numerically when it's more relevant. Now, these orbital distances, I'm going to call this r. If r could be absolutely any value in the universe, I mean just, it wasn't restricted in any way, then the energies of the orbits would have no restrictions on them. So basically this electron could absorb very little energy and move out, in my picture, just like 1 centimeter or 1 millimeter or 1/10 of a millimeter, and then fall back down. It's an important thing to realize that if r could be any value, then the energy of the orbit could be any value, which means the photon energy given up, because when an electron falls down in orbit, the photon energy could be any value. Because you'll see later in the video, the photon energy ends up being the difference in energy between this orbital distance, or this state, I'll say, and the outer one here. So if in fact r could be any value, that would imply the energy of the state could be any value, which would imply the energy of the photon could be any value. But what that would imply then is that if you looked at the radiation coming from a hydrogen atom, you would see a continuous spectrum, much like I have over here in this color wheel, that all the different frequencies would be represented. Because again, if the energy can be any value, then the frequency could be any value. Right? So this is kind of an important thing to understand here, that this is the motivation for why we're looking for a new theory to describe the atom. If this radius can be any value, then the energy can be any value. Energy of the orbit, the energy of the photon could be any value, the energy of the frequency could be any value. And remember that the frequency dictates the color. That implies over here, if you looked at the light coming from a hydrogen atom, you would see a continuous spectrum, you'd see everything. But that's not what we observe. That's not consistent with observed phenomenon. So if you think back earlier in the video when I talked about spreading the light out and seeing only the bands. So that's the motivation for why we're looking for a new theory of the atom. So I'm going to take a moment here and kind of clean my pad up, and we're going to talk about a better theory of the atom here. All right, so clear that. So Niels Bohr came along, and he was looking for a way to kind of fix this, and he started with what he calls the Bohr hypothesis. And the Bohr hypothesis is that the angular momentum of the electron is quantized. So if you have my college physics class or my calc-based physics class, hopefully you're somewhat familiar with angular momentum. I'm just going to do a quick little shortcut on it. Angular momentum is usually denoted with the letter L, and you get it by taking your translational momentum, mv, meaning that over here, this electron, it has some sort of speed v, let's say. Therefore, it has a momentum equal to mass times v, and multiplying by r, the distance to the nucleus here, that makes a right angle of v. So this is now an angular momentum. Now, the angular momentum being quantized, what quantized means is it comes in discrete chunks. So in this example, what it means is that the angular momentum comes in discrete units. The units are called h bar. There's a numerical value for this that's in your textbook somewhere, and I'll write it down later in the video. It's not important for now. And if the angular momentum is quantized, that means it has to be some multiple of h bar. So what we would say is that the angular momentum is equal to n times h bar, where n is an integer. 1, 2, 3, etc. That's what we mean by quantize or quantization. So the Bohr hypothesis is that the angular momentum, right, r times mv, is quantized. That means it's equal to some integer times h bar. Okay, now what we're going to do is we're going to apply some physics to this electron going round and round and round, and we're going to incorporate this what's called the Bohr hypothesis. So the first piece of physics I'd like to incorporate is this, right? If we draw a free body of this electron, there's only one force acting on it. And that force is an attractive force, and that's called the Coulomb force. And hopefully you've studied the Coulomb force, but the Coulomb force in general is equal to K Q1 Q2 over R squared. Well, the charge of an electron is the same as the charge of a proton, other than the sign on it. And the sign is just used for things like force directions, which I have. So I'm going to write that force kq squared over r squared. All right, so this is Coulomb's law. The charge between a particle is k q1 q2 over distance squared. Now, for this problem, as this thing goes around and round, you need to recognize that it is in fact accelerating, even if the speed is constant, right? It's accelerating because the velocity is changing direction here. What we have is a centripetal acceleration. So if you haven't seen, or if you're unfamiliar with centripetal acceleration, you can go back. I've got plenty of videos on that, I'm sure. All right, so when we apply Newton's second law, which is net force equals ma, right, the net force on the system is the Coulomb force, kq squared over r squared. And the acceleration, because it's a centripetal acceleration, can be written v squared over r. So Newton's second law gives this relationship here. And what I'm going to do here is take note that there's two r's here on the left, one on the right. So I'm going to just cancel one of them and store the resulting equation over here. So we got kq squared over r is equal to mv squared. Right. Here's where we can now incorporate the Bohr hypothesis. And what I want to get out of this is a value for r. And you'll notice that we've got an mv squared, and the v is what I want you to focus on right now. I want to try to eliminate the v, and I'm going to use the Bohr hypothesis to do that. All right, v from the Bohr hypothesis is equal to nh bar over r times m. Right, just by solving this for v. And if we sub that into here and rewrite the equation, so now we got kq squared over r is equal to m times v squared, v being nh bar over r times m. And again, that's being squared. All right. Now, what I want to do now is solve this equation for r. And let's see, how about we do this next line? Kq squared over r equals m n squared h bar squared over r squared m squared by the time we square all of this. Now you'll notice we got two r's on the right and only one on the left. One of these will cancel, leaving us with one on the right. And what I'm going to do is I'm going to move that over to here and then divide by q squared. So our new line here is going to read r equals n squared times m h bar squared over kq squared. Make sure that's right. Oops. 1m on the top, 2 in the bottom. My apologies, that m should be downstairs. Go ahead and get rid of that. I think that's right. Let's see, r kq squared on the bottom, n squared h bar squared over m kq squared. Yep, this is right. Now, very important thing to realize, I'm going to clean that up a little bit. This is r equals, now remember n is just an integer, so this is going to be n squared times, right, h bar squared over k q squared m. This is all a constant, a number. You can look up these values. These are all in, if you're in a physics test, you can look these guys up, no problem at all. And I'm not going to take the time to do this right now and run through the math. I'm just going to write down the results. You look up every one of these constants. This is the Coulomb constant, 9 times 10 to the 9th. This is the charge of an electron, 1.6 times 10 to the minus 19th. Mass of an electron, h bar here. Look these all up, run a value here, and what you get is n squared times a value of 5.29 times 10 to the minus 10th meters. This value right here is called the Bohr radius. It's usually written something like a sub r, I think, or a sub o. I'll just call it a sub o for the video here. Important thing is that this is a fixed numerical constant that we can look up called the Bohr radius. I'm just going to call it a sub o here for the rest of the video. It's important to know that this is now a known value. So what we have now, it's very important to realize here, and I'm going to store this equation up here. What we have is that r is equal to n squared times a sub o, where a sub o is a fixed numerical value. And what that means here is that the radius can't be just any old radius, right? The radius can be 1 times a sub o. However, if this electron moves up to a higher orbit, the second orbit is going to be 4 times a sub o, because the second orbit, if I put the second integer there, 2 in, and square it, you get a 4. The third orbit out is going to be 9 times a sub o, and so forth. So this number, the n, is called the principal quantum number, and what it has done now, it has given us a numerical equation here that tells the allowed orbits for the electron, or the allowed orbital distances for the electron in a hydrogen atom. And all atoms will obey similar types of laws. It's just that these a sub o's will be different, because different atoms are going to have different numbers of charges and so forth. So I'm going to just kind of store this for now. I'm going to take a moment, pause this video here. I don't want it to get too long. Clean up this, and we're going to talk about hydrogen in a bit more detail and what happens when photons interact with it. Hi folks, okay, so I'm back here, and I've obviously cleaned it up and changed my picture quite a bit. So I've kind of modified my model of a hydrogen atom. So now we've got this nucleus, we've got this electron orbiting around. But now, as a result of the previous work here, we found that the orbital radiuses, remember, were equal to n squared a sub o, where the a sub o is called the Bohr the Bohr radius, 5.29 times 10 to the minus 10th meters. So I kind of modified my picture here. Here's our first shell. This distance would be 1 Bohr radius, a sub o. The n equals 2 shell, this would be the orbital distance, which would be 4 a sub o. Now this is not, I should have probably put this quite a bit further out, but the third orbital distance would be this one, which would be 9 a sub o, and so forth. And I'm getting that by putting different values of n in. 1 squared a sub o, 2 squared a sub o, 3 squared a sub o, and so forth. And these are the allowed orbits, or the allowed shells for this electron. Now I'm going to talk a little bit now about the allowed energies. So the energy of this electron as it goes round and round, if you think about the work energy theorem, which if you're one of my students, we've written this out many times, is the sum of two things. It's the kinetic energy plus the potential energy. So that means that it's equal to 1/2 mv squared minus kq squared over r. Now the kq squared over r, here's where it's coming from. If you think back, or if you go back to my previous videos about the potential energy of a point charge system, all right, the potential energy of a point charge is k q1 q2 over r. All right, and because the q's are the same, I just wrote it q squared because it's shorter. The potential energy here would be negative because one of these charges is negative. And we can now take the Bohr hypothesis and our previous results here to try to come up with an equation here that's a little bit useful, I'll say. All right, so first of all, I'm going to get rid of this v. So this is going to be 1/2 m, okay, v. The v, again, we can get from the Bohr hypothesis. V is equal to nh bar over rm. So nh bar over rm, and that's being squared. All right, and then minus kq squared over r. Whoops, I got to back up. That was not what I wanted to do there. I'm sorry. That is true, but not what I want to do. I'm going to back up. All right. If you go back to the video slightly, we had written out Newton's second law, and Newton's second law, remember, was kq squared over r equals mv squared. I'm sorry. kq squared over r squared equals mv squared over r. This was the Coulomb force, kq1 q2 over r squared equals ma. This, we can divide an r out to get this relationship. kq squared over r is equal to mv squared. And this is what I want to use on this term right here. So you'll notice mv squared, mv squared. So this is equal to 1/2. And the mv squared can be written kq squared over r, and then minus kq squared over r. And you'll notice it's 1/2 kq squared over r minus kq squared over r. Those add to minus kq squared over r. All right, so we have an expression now for the total energy of the electron as a function of r. Now, from before, we have r in terms of n and the Bohr hypothesis. So this is equal to minus kq squared over r equaling a sub o n squared. And now what I'm going to do here is notice that this is all a constant, and the n can be factored out of this. So this is going to be minus kq squared over a sub o times 1 over n squared. And what we have now is an equation for the allowed energies in each orbit. Now, video is getting a bit on the long side, so I'm not going to show the calculation here. I'm just going to write out the results. If you take all the numbers here, right, 9 times 10 to the 9th, 1.6 times 10 to the minus 19th, and the Bohr radius, 5.29 times 10 to the minus 10th, and you calculate a value, you're going to get a value. It's very, 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 very small. It comes out to be something times 10 to the minus 18th. So you get that value, and then you convert it to EVs. Remember that there's 1.6 times 10 to the minus 19th EVs per joule. Out will come minus 13.6 EVs. I'm going to leave that to an exercise to the reader here. Take these values, 9 times 10 to the 9th, 1.6 times 10 to the minus 19th, square it, divide by the Bohr radius, 5.29 times 10 to the minus 10th. You're going to get a value or a number. Take that number and multiply by this conversion factor. Out will come minus 13.6 EVs. So our allowed energies are minus 13.6 EVs times 1 over n squared. So now what we have is an equation for the allowed energies for the electron in a hydrogen atom. So if you give me a moment here, I'm going to kind of clean this up and just try to summarize all of this. I don't need any of this for the summary here. All right, let me get this down to the really nitty-gritty important stuff here. So, important thing number 1. Okay, an electron orbits in known states. You have a first state, a second state, a third state. These are called, right, the 1, the 2, the 3. These are called principal quantum numbers, n. Okay. Important thing number 2. The Bohr hypothesis. angular momentum quantized, RMV equals NH bar. This is not, we're not going to use this much for solving problems, but I do think it's important to fundamentally understand where it came from. 3. The allowed orbits for a hydrogen atom are equal to a sub O n squared, where again the a sub O is 5.29 times 10 to the minus 10th meters. Now this is true for hydrogen only. Okay. 4. The energies, the allowed energies per orbit, or of each orbital state, is minus 13.6 EVs times 1 over n squared. Now, this has some consequences here. I'm going to go through some numbers. So the n equals 1 orbit. Oops. If n is equal to 1, that means the electron carries an energy of minus 13.6 EVs, or electron volts. If n equals 2, that means the allowed energy is minus 13.6 over 4 EVs. If n equals 3, the energy of that electron is minus 13.6 over 9 EVs, and so forth. There's really no end to this. We could keep going. Now, just the video is a little longer than I want. Let me just do some final comments here. How does the electron change orbital states? By absorbing energy. So if this electron absorbs enough energy, it can move up to the second state. And now this is what its energy would be. The electron, when it goes back down, will give up a photon of energy equal to the difference between these two states. And again, I'm going to do another video on that because this thing's gotten longer than I'd like. But let's see what else, really important things. So let's see, mechanism for the electrons moving up, absorbing photons. Mechanism, when they go back down, they give up photons. Principal quantum number, Bohr hypothesis, allowed orbits, orbital distances, allowed energies. I'm going to save examples for another video because this thing's gotten a little longer than I'd like. Hope you enjoyed this. Have a great day.